The next factor after the rainfall erosivity is the soil erosivity we have to take into account in the universal soil loss equation. And this is the soil erosivity for Bavaria in Germany. You see here some areas which have a large soil erosivity and some areas which have smaller soil erosivity. And we want to have at the end of this lecture something like an idea on soil erosivity. How does it work? So first of all, what was soil erosivity? It was a factor in the universal soil loss equation of Wischmeyer and Smith. We had a lot of factors here. We had the rainfall factor, we have the soil factor, which we want to discuss in this lecture. We have the slope factor, the length factor, the crop management factor, and the protection factor. These are the factors in the Wischmeyer-Smith equation, universal soil loss equation, and we want to have a deeper look on the soil erosivity factor. So first of all, what is a soil? A soil is a very complex matter. It helps us to survive. It's absolutely important to survive, and because it is the fundament for agriculture. And we can describe a soil as physicists, first of all due to its soil texture. The soil texture tells us how much sand we have in a soil, how much silt we have in a soil, and how much clay we have in a soil. So let us give an example, and this is a classical scheme here. This is in German silt, so think about silt here, and this is the German word for clay. So here we have the clay content axis, and here we have the silt content axis. And let us just have an example. So when we are, for example, with a soil more or less here, then this soil has something like 55% of silt in this time. And when we look here, then we have 30% of clay here. 55 plus 30 makes 85%, and this means that the sand content is 15% because we have to add it on 100%. So this is the idea how it works. When we know two parts of a soil, when we have the clay content and the silt content, we can calculate the sand content by dividing these two fractions from 100. So this is the idea of the scheme. So when we are here, for example, this line says that there is no sand in a soil. So let's have a look here. For example, when we are here on this line here, on this diagonal, then we have at this point 80% of silt and 20% of clay. This means no sand here. When we are here at this point is only sand. This is a total sandy soil which has no other stuff in it. It is just sand, as you can see here, and the name of the soil is SS. It is sandy sand, because here we have no clay and no silt in the soil. So this is the idea how to read such a diagram. This is the first thing how we can distinguish different kinds of soils due to the soil's texture. The next thing is the vertical structure. Different kind of soils have different vertical structures. We have something like a vegetation on a soil, then we have different horizons of soils. I don't want to go into detail here, the ABC horizon, and then we have something like the stones under a soil, and everything in between. There's something in between, more or less biological soil and a more or less geosoil, which is only which only contains stones here. So this is a vertical structure, and we can also talk about soils looking on the vertical structure. And the final thing is we have the biology in soils, and we can also distinguish different kind of soils with the same soil texture and the same vertical structure due to their due to their biology. So this means that soil is a very complex thing. And this means, again, that the factor K here, we cannot have something like a general formula which determines K here. This is a very important thing. Every formula on K is just an idea how large K should be. And I would like to present two formulas in this lecture. The first formula comes from the so-called Russell, the revised universal soil loss equation from I don't know from which year, 1978, Wischmeyer-Smith, I think, was Russell. And they said that we can calculate K according to this formula. And this formula for me is very complex. I don't like it very much. I prefer another approach. Yes, this is also here Wischmeyer-Smith in the Russell in the revised universal soil loss equation. I prefer Williams. Williams is an approach which looks at the sand, silt and clay content and also on the biological content and calculates the soil erosivity only due to the soil texture. So as I said, this is of course not absolutely correct, but it gives us a first idea on how large is K. And the formula they propose is this long formula. So in this formula you have different kind of M of sand, M of silt and M of clay, and these are the percentages of sand, silt and clay, and you have to introduce them in this kind of formulas. You have to calculate all the stuff here, and then at the end you get a combined formula. We have to multiply all these things here, and then you get a formula for the K factor here. And the result is looking like this. I will show you the result. This is the clay content, and this is the silt content again. So here at this point we have only a sandy bottom. A sandy bottom here at this point. And a sandy bottom only consisting of sand has a very low soil erosivity in this content, because sand are very large sediments. And when we have only clay here at this point we have only clay, then we have quite a large erodibility, because clay can be very easily eroded. And when you look at this formula here, when you plot it in that way, you get such an idea of how large is the soil erodibility. But as I said, this is only a first idea which is only dependent on soil texture and not on biology and not on the vertical structure on a soil. So in order to apply it, you can stop this video here. This is a function according to Williams I wrote in MATLAB. You just introduce here the contents of sand, silt and clay, and the organic contents is also taken into account in percentage, and then this function calculates the soil erodibility. If you want to do it for yourself, you just stop the video here and program it for yourself. So this is the idea of Williams, and this was the idea of Wischmeyer and Smith. So I like Williams I like Williams more than Wischmeyer and Smith at this point, but as I said, it is also not exact, because every soil, especially in the change of the year, looks a little bit different. In Bavaria we have some tabulars. Which allows the farmers to calculate their soil erodibility. I don't want to go into details. They have to look at the soil contents as well. Then they have to look at what they do with their soil, whether it is crops or whether there is meadow on it or whatever. And then they look into this tabular, and then we'll find out for stony soils what kind of soil erodibility is this, and for fine soils, and then they have to multiply these two factors, and then they get the soil erodibility. Such kind of methods with tables are also will also be used in other countries in the world, and you have to look for your country how the soil erosivity is determined over there, But as I said, these two formulas in the beginning of the lectures are also quite well. So this is the soil erosivity in Bavaria, and as I said, we have a large erosivity here around the Isar and the Danube River here in this area. There, the soil erosivity is quite large, and in other areas, especially in the stony areas of the Alps, we have nearly no soil erosivity because yes, there the mountains are more or less stony and there is no soil erosivity. Also in these areas of Bavaria here we have lower soil erosivities, and then you can calculate the total erosivity. The total erosivity then is calculated in that way that we multiply the rainfall erosivity with the soil erosivity, and then we get something like the total erosivity in an area as a first idea. And then of course, according to Wischmeyer and Smith, we have to determine also the slope factor, the length factor, the crop management factor and the protection factor. And when we do not know this kind of factors, we set them to 1, and then we get a good estimate for the soil erosivity.